Okay, hello once again, Algebra students. It's your fearless leader, Dr. J, about to wrap up the school year soon. We got 3 more things I want us to get through. Okay, 3 more things in 2 weeks, and I think we're going to be just fine. So today I want to go over the first thing. All of us is going to be dealing with it's called quadratics, and we're just going to touch the basics of quadratics because what I want to do is set the table. You'll see a little bit of quadratics in geometry, a little bit, but where those of you that go on to take Algebra 2, you'll see a lot more of this. So I don't want you to have unfamiliarity with this topic, okay? So the first section's 9.1. I'm starting here on page 480, and it is properties of radicals is the highlight or the name of the chapter, all right? Properties of radicals. I'm going to lecture just a little bit, work through some problems with you, and then I'm going to pause for you to work through some problems as well, okay? So, the first thing it says here is a radical expression is an expression, a mathematical phrase, right, that contains a radical. It contains a root, like a square root sign. It's called a radical expression. An expression involving a radical with an index n, remember n is the power of the radical, is in its simplest form when these 3 conditions are met. Number 1, no radicands have perfect nth powers as factors other than 1. I'm not really going to worry about that one. Number 2, no radicands contain fractions. And finally, no radicals appear in the denominator. All right? So those are your 3 basic rules when you're trying to figure out whether you should simplify it or not. And so we're going to show you, you're going to have to use some mental math to figure out whether you can reduce a radicand that you'll see as an expression, right? So this first core concept, it's the product property of square roots. The square root of a product equals the product of the square roots of the factors. That's a lot of words. Please look at this or have your book open and look at it as I go along, right? So we've got this expression, I'm going to write it a little larger up here. The square root of 9 times 5. Okay? You can rewrite that as the square root of 9 times the square root of 5. Why do you do that? Because you can then reduce it, right? You all should know by now the square root of 9 is 3. So this can then be rewritten as 3 square root of 5. Okay? That's your introduction on how to reduce radicals. So we have this first example. Let me slide it up just a little bit. It's asking us to reduce, let me see if I can write it. I'm going to choose a different color. This one's a little bit light. It's asking us to reduce the square root of 108. Hopefully, you all recognize that that is not a perfect square, right? 108 is not. 121 is close, and on the other side of that is 100. So it's not a perfect square. However, embedded in that is a factor that is a perfect square. And that's where you have to figure out what numbers divide into this number. Okay? I'm going to show you the long way of going about that to help you arrive at the answer, okay? So you should be able to tell, if you recall, how you can tell if something's divisible into something is, like for instance, if you want to know if it's divisible by 3 or by 9, add up all the numbers in that number. So it's 108, 1 plus 0 is 1, 1 plus 8 is 9. Is 9 divisible by 3? Yes, then so is this number. Is 9 divisible by 9? It is. So this is also divisible by 9. So I'm going to rewrite it. Square root of 9 times, and 9 goes into that 12 times. So I've got the square root of 9 times the square root of 12. Okay? Now, we already know the square root of 9 is 3, so we can be done with that. Recognize 12. 12 you can split into the square root of 4 times the square root of 3. Right? Because 4 times 3 is 12. And then you know that the square root of 4 is 2. So now I can rewrite this. 3 times 2 times the square root of 3. 3 times 2 is 6. Square root of 3 is a prime number. You can't do any more with it. So the square root of 108 can be reduced to 6 square root of 3. Now, in the book, they just assumed, if you look at the example written in your book, that you would be able to realize that 36 divided evenly into 108. And most of you are not going to realize that. So that's why I was showing you how to factor it, okay? So what they showed in the book is you can pull out the square root of 36 times the square root of 3. Square root of 36 is 6. And we end up back at the same point. Okay? I just wanted to show you some other ways to get to that same, which is going to make more sense to you. All right, the second example is square root of 9x cubed. Follow me here. The first thing you should be triggering when you see this is you go, well, I know that 9 is a perfect square, so I should be able to take the square root of that, right? We should know that. But also realize you can split things that are multiplied underneath radicans. You can split. So we have the square root of 9 times the square root of x cubed. Okay? So right away you know this is 3, and now I can rewrite this as the square root of x cubed. However, you're not done. Remember your rules of exponents. You can split this. 3 times the square root of x squared times the square root of x. Why do you do that? Well, because this squared term gets reduced and eliminated by the square root sign, leave me with 3x times the square root of x. And that is your simplified answer from here. You started with the square root of 9x cubed. You ended up with 3x times the square root of x. Okay? Just recall x squared, any variable squared, any term squared with a square root gets rid of the square. Okay? That's all. The square root cancels out the square. All right. So we've arrived here at the bottom of 480 with 4 practice problems for you. So at this point, please pause and work through those practice problems. Pause. All right. So let's take a look. The first one is the square root of 24. So I'm trying to think about, are there any perfect squares that divide? Oh, pardon me, I've got to let Liberty in. Are there any perfect squares that divide into 24? Okay, clearly you should know 4 divides into 24 and 4 is a perfect square. So I could rewrite that as the square root of 4 times the square root of 6. Okay? Now the square root of 4, of course, is 2. Square root of 6. Are there any perfect squares that divide into 6? The only factors of 6 other than itself are 2 and 3. Neither one of those are perfect squares. So you are done. Your simplification on number 1 becomes 2 square root of 6. All right. Number 2, they threw a negative at you. As long as it's on the outside of the radical, when it's a square root, that's fine. Just set it aside. Remember it's there. Don't worry about it right now. We want to put it aside. So what we're asking ourselves is, do I know any perfect squares that divide into 80? Now you may have said right away, well, the square root of 4 does, right? So that would give me the square root of 4 times the square root of 20. Don't forget your negatives hanging out here. Which becomes 2 square root of 20. So then what you need to ask yourself though now is, are there any factors of 20 that are perfect squares? As you pause to think about it, 4 can still divide into that. So I can rewrite that again as 2 times the square root of 4 times the square root of 5. Because 4 times 5 is 20. So now the square root of 4 is 2. I have 2 times 2 is 4. I'm now down here with 4 square root of 5. Don't forget your negative. Bring that over. So it's negative 4 square root of 5. That's the answer to 2. Number 3. We've got the square root of 49x cubed. Most of you right away know that 49 is a perfect square, right? That's great. Let's split it like we did in the example. square root of 49 times the square root of x cubed. Clearly this becomes 7 square root of x cubed. But again, remember we can split the variable. So we're going to split it, square root of x squared times the square root of x. Because there's a total of 3 in there, right? I have 2 here and 1 there. The square root cancels out the exponent, leaving me with 7x times the square root of x. And you're done. Lastly, number 4. Square root of 75 into the 5th. This is going to be multi-steps. So again, first we're going to split square root of 75 times square root of n to the 5th. Let's work with the number first, right? What perfect square divides into 75? You should have arrived at 25. So we split this. Square root of 25 times the square root of 3 times the square root of n to the 5th. So I'm going to reduce here first. Right? Square root of 25 is 5. Square root of 3 times the square root of n to the 5th. Now, to shorten this, okay, we've got 5 n's here. So we're going to split them up like this. Not forgetting about our 5 square root of 3, we're done with that. Times the square root of n squared times the square root of n squared times the square root of n. That gives me 5 total n's, right? 2 here, and 1 there, for a total of 5. Again, the square root cancels out the exponent. I'm left on the outside with 5 square root of 3. Let me do that again. 5 n squared square root of 3 square root of n. And then to make it look right, let's bring those back together. 5n squared times the square root, I need to put the parentheses there, times the square root of 3n. Okay? Ooh, that was ugly. Love it. All right. That's that. Can you guys bear with me for 5 to 10 minutes? All right. The next is the quotient property of square roots. This is not really troublesome at all. Okay? In the what it says here, if you have a square root over a fraction, you can split that root in both numbers, the top and the bottom number, and reduce from there, right? So if you look at this example they gave you, it was the square root of 3/4. Split the square root, so it's the square root of 3 over the square root of 4. Square root of 3 cannot be reduced, square root of 4 is 2. Easy enough. Okay? And they're showing by algebra, I'm not even going to rewrite it. Square root of a over b is the same as the square root of a over the square root of b. Okay? Alright, let's see the next page. So here's the quotient property of square roots. Right? So notice here, you've got the square root of 15 over 64. You split the square root towards the square root of 15 over the square root of 64. Square root of 15 cannot be reduced, but the square root of 64 is 8. And now that's your simplified form. Then in example B, they had square root of 81 over x squared. They split the square roots over both. The square root of 81 is 9. The square root of x squared is just x. It's pretty straightforward. That one's not too tough. And then the last thing, we might do one more thing after this. I'll have to see when we get there. This is the properties of cube roots. Okay? A little bit more tricky. So they ask you for the cube root of negative 128. Okay? Which in and of itself is not a perfect cube. But 64 goes into that twice, and 64 is a perfect cube. Even negative 64. So they split it up. Then they put the cube root over both. The cube root of negative 64 is negative 4. And the cube root of 2 brings down. Here they do it with variables x to the 7th. Okay, then they split it up. They split the x's into x to the 6th times x. Cube root of 125 is 5. Cube root of x to the 6th, remember when you have it raised to a radical, it's actually into a fraction. You divide 6 by 3, x squared, and the cube root of x. Okay? Let's see, so some examples. I don't want you to do all of these. What am I going to have you do? Do the ons? Yeah, let's do the odds. Great. We're going to do the odds. So go ahead and pause here and do the odds. I'll come back. All right. Number 5. The square root of 23 over 9. We split to the square root of 23 over the square root of 9. That square root of 23 is a prime number. Nothing we can do with that. But the square root of 9 is 3, of course. So the answer is square root of 23 over 3. Number 7. Split it up. Square root of 36 over the square root of z squared. Square root of 36 is 6. Square root of z squared is z. That one's easy. Number 9, the cubed root of 54. Cubed root of 54. Okay? That may have taken you a little bit. This is where knowing your cube roots helps you. This is split to the cube root of 27 times the cube root of 2. Cube root of 27 is 3. Cube root of 2. That's your answer. 3 times the cube root of 2. And then number 11. Cube root of a over negative 27 equals the cube root of a over the cube root of negative 27. Cube root of a is done. Nothing we do with that. Cube root of negative 27 is negative 3. So it's negative cube root of a over 3. Okay, that was 11. I know there's one more concept I want to show you before we're done. And it's when you have a radical in the denominator. They call it rationalizing the denominator. That sounds so scary, and it's not. Okay? So in the example, you have square root of 5 over the square root of 3n. You cannot leave a square root in the radical. You have to get it out. So what you do to get rid of it is you multiply it top and bottom by that term in the bottom. Okay, so we're multiplying top and bottom by the square root of 3n. Then you rewrite that as the square root of 15n, because the square root of 5 times the square root of 3n equals the square root of 15n over the square root of 9n squared. Okay? They split those up at the bottom. You don't necessarily have to do this step if you can just recognize the square root of 9n squared is 3n. So I have the square root of 15n over 3n. Okay? They do the same thing with the cubed root. It's just a repetitive thing of that. It's better if we go, we're not going to do conjugates. That's a complexity I don't want to get into right now. So what I'd like you to do is, let's do 13 through 16, okay? 13, the top row, 13 through 16. Last thing I want you to do. So go ahead and pause here, work on those, we'll be right back. All right, we're back. 13 is 1 over the square root of 5. I can't have a radical in the denominator, so to get rid of it, I multiply top and bottom by the square root of 5. That gets rid of the radical in the bottom. It becomes the square root of 5 over 5. Okay, square root of 5 over 5. 14, square root of 10 over the square root of 3 equals, we times that by square root of 3, top and bottom. That leaves us with the square root of 30 over 3. Do a quick check to make sure you're not leaving out any perfect squares that are divisible into the square root of 30. 130, 215, 5, 6. Nope, done. Square root of 30 over 3. 7 over the square root of 2x. I'm going to multiply top and bottom by the square root of 2x. Okay, again, that crosses out the square root signs. On the top, you have 7, square root of 2x. On the bottom, you have 2x. Double check to make sure you can't reduce. 7's a prime number. It's not divisible by 2, so you're done. Okay, 7 square root of 2x over 2x. Last one. Square root of 2y squared over 3. Okay, Okay, so we're going to split those first. Square root of 2y squared over the square root of 3. Going to multiply by the square root of 3, top and bottom. That's going to give me the square root of 6y squared over 3. 6 is only divisible by 2 and 3. Neither one is perfect square, so this is your final answer. Square root of 6y squared over 3. If any of these are confusing, I know I went through these relatively quickly. Please recall, push the white arrow on the blue dot and it'll play it out for you again in a slower fashion. All right? And we'll go over them tomorrow in class. So that's all I want to go through with you. Let me double check what I'm telling you. I know there's a couple of the concepts in here. But honestly, just solving real life problems. Who wants to solve real life problems? Oh, conjugates. I'm definitely not going to deal with you with conjugates. You all are going on to Algebra 2. That's something that they can cover with you in Algebra 2. You won't need that for geometry that I recall. I don't recall using conjugates, and Liberty's not going to remember it for sure no matter what. But, anyway, that's where we're going to stop at right there. That's the first lesson, 9.1, evaluating radicals. All right? See you guys.